Good afternoon, everyone. I hope you're faring well wherever you are. Cameras on, please, so I can see your faces. Okay. Thank you. All right. Okay, so let's just start off by recapping. Oh, yes, so I uploaded the lecture notes from last lecture, so you will find that in Brightspace, so you can take a look at that for all the information. So as for today, I thought we would let's just first recap. So I'll just share my screen. Right, so we were talking about static electricity, and we sort of started off by just talking a little bit about some common everyday examples, ranging from this girl rubbing her hair on a balloon and hair getting attracted to it, to in winter getting an electric shock when you touch something. Other examples are with, for example, this person, you have laundry that's just come out of the dryer, then things can sometimes stick to you, and plastic and things like this. So what we want to do here is to really try to understand these things, and I think probably most of you are pretty familiar with static electricity, but we're kind of trying to pin down some of these details, right? So for example, why does it, why does this hair stick to a balloon, after you start to rub the balloon on your hair, why should it do that? I mean, okay, there's some electricity, and as we've seen, like charges repel and opposite charges attract. Okay, so that's one level of explanation, but then, why does that happen in the first place? And, if once you start to go a little bit deeper, you sort of start to realize that perhaps you don't understand everything there is to the phenomenon. So even though this is like quite simple basic stuff that you might see, at some level it's hard to really understand why. So yeah, so we looked at a couple of different examples, like this kid sliding down a slide. Of course, so this is a bit similar to the the rubbing effect. So somehow rubbing generates this electricity somehow. And this was a little bit different because this one was, so we figured out that this was due to an imminent lightning strike, potentially, right? So clouds in the sky can accumulate a lot of charge, and then there could be a big charge distribution within the cloud, the negative side of the cloud being close to the ground. And why does that happen in the first place? Well, it's because, again, because of some kind of rubbing effect. So you have this large snow particle, graupel, that falls in the cloud. It hits all these particles and it accumulates charges, or they exchange charges, right? So we saw a little video about how that happens. Yeah, and so what we want to try and understand are some of these questions, like, so why should rubbing do anything? I mean, what's so significant about rubbing that produces static? Why does these things only stick to the person as opposed to repelling? You might think that sometimes the charges might repel each other instead of sticking, right? Where do the charges come from? And what are these sparks that you sort of get? I mean, you intuitively, or you just know from common knowledge that this is something to do with static electricity, but what's exactly the process, and why is this not lethal whenever this happens in winter? So we're trying to answer some of these questions today, I hope. Right, so let's just go back and do a little bit of a history lesson first. So history of static electricity. So I think the first recorded record of this kind of phenomenon was by this Greek philosopher, Talos of Miletus, around about 600 BC. Now, maybe there's even earlier accounts, in say China or elsewhere. But well, at least this is the earliest one in Western recorded history. And basically what he noticed was that if you have a piece of amber, amber is the stuff that comes out of trees, right? So if you make a cut in a tree, some sap, that's the juice of the tree, comes out, and then it solidifies, and then that solidified chunk kind of forms like a kind of a hard rocky substance. And so you would have seen in movies like Jurassic Park, where some animal is caught in the amber, and then it's extremely well preserved, right? So it's sort of like a perfect way of capturing and having a record of certain things. But anyway, it's sort of like a plasticky kind of substance. So if you rub it against fur, then it starts to pick up static electricity. And so you can see an example of this where it's picking up pieces of feather. Then thousands of years later, I guess, the French guy Charles Francois de Cisternay de Fay, okay, pronouncing it very well, but so in 1733 noticed that there were two types of charge. So I think the way that he made this deduction is again by rubbing certain things and then looking at how they attract or repel each other. So if you have two materials, then, and if they're the same type of material, then often it tends to produce the same sign of charge. So these days we take it for granted that there's two types of charges, there's positive and negative, but of course somebody had to discover that at some point. And so by looking at the whether things attract or repel, you could figure out that there are basically two types of charges. So there's positive and negative, although he didn't name it that way, but they noticed that there were two types. And possibly the most famous guy in relation to this stuff is Benjamin Franklin. So he was the guy that named it like positive and negative. So the French guy already realized it was like two types, but he sort of made the kind of convention of calling certain substances positive and some negative. And so if you're wondering, how do they know which is positive and negative? Well, essentially it depends upon the substance. So if you rub a glass rod with a silk cloth, then basically it's completely dependent upon the material, so that the glass rod tends to become positively charged and then the silk cloth negatively charged. So basically, even if these things start off as being neutral, then the charges sort of separate and they accumulate on each other. And it depends basically on the substance, right? So it depends on what material is actually made of. Similarly, so animal fur against rubber, this also produces static electricity, but in this case, the rubber actually accumulates a negative charge, and then the animal fur accumulates positive charge. So something dependent upon the material. So some materials just tend to become like either plus or minus, right? It just depends on what the stuff is. And you might know that when you have an electrical current, that actually the things that actually flow are actually electrons. And so there's this whole thing where if you write down a current and say it's going, say this way, and you say, okay, the current's going, in this direction. Actually, what's happening is that negative charges are flowing in the opposite direction. Who knew that piece of fact? Do you learn about this in school or anywhere? Okay, judging from the response, I'm not sure people knew that fact, but basically, if you have a current, then actually the things that flow are the negative charges, and the positive charges actually do not actually move. And this is a bit of an unfortunate kind of convention, which traces its history all the way back to this point when Benjamin Franklin named, the things positive or negative. So in a way, there was like a 1 in 2 chance of getting it right, and then he kind of got it wrong, and then now everybody has to live with this forever, which is a kind of a weird thing. But of course, he didn't know that it's only the electrons that actually move. It's actually, and the positive charges are actually fixed. That only was discovered much later. So this kind of seemingly arbitrary choice means that we kind of have to live with this this kind of convention, right? But okay, so right, so this kind of establishes that there's 2 types of charges, positive and negative, and then some materials tend to attract these charges, one type of charge more than the other, right? Okay, and so what are these actual charges? Well, what they basically are either electrons. So the negative charges are typically electrons, and electrons are basically one of the fundamental constituents of matter. So if you have an atom, then they are made of an electron, which is kind of, you can picture it as orbiting this nucleus. Nucleus is made of protons and neutrons. So protons are like these positively charged things, particles, and then neutrons are neutral particles that they are sort of bound together inside the nucleus of an atom. Now this atom is not drawn to scale, so actually the electrons are like way further out than than this picture kind of suggests. So the size of the nucleus is really tiny compared to the whole atom, but the actual mass of an electron is much lighter than the nucleus. And so this is basically why we can picture the whole thing as the electrons orbiting the nucleus, because just like in our solar system, the sun is like way heavier than all these other planets, right? It's way heavier than the Earth and so forth. So we kind of see it as that the Earth is sort of orbiting the sun, but actually, that's basically because the Earth is so much lighter than the sun. Okay, so Haihan has said, really, I forget, I didn't see what point you wrote your chat. What was the point that you're commenting on, Haihan? Haihan, you there? Oh, okay. So what point, what are you talking about, Haihan? Like, you're saying, I think it's only a model. So what do you mean? You can unmute yourself. It's a bit easier to talk than type, I think. Ah, yes, Rutherford, yes. Right, so yes, Rutherford did an experiment where he, well, that's good. I like to go on a tangent. Yeah, so he did an experiment like this. So he had like gold foil. So this is gold. And gold foil, you can use gold foil because you can make extremely thin layers of gold. I'm not sure why gold is so good at this, but for some reason you can make extremely thin layers of gold. So, this is why they use it in materials like, paste it on the surface of temples and stuff like that. So even though, it looks very expensive, actually the layers of gold are extremely, extremely thin. So you're not using much gold. Anyway, so the number of atoms thick, the gold can be extremely thin. And then if you shoot some charges, I believe they were, I think they're electrons, right? So if you shoot electrons. If it's wrong, then somebody please tell me. And if you shoot electrons at this gold film, then what he found is that this sometimes bounces, in some crazy kind of directions like this. So it can bounce even right back 180 degrees towards the detector. And I don't know, it must be positively charged, because otherwise it wouldn't do this, right? I think it must be it's either proton or electron. I'm thinking it's actually proton now. So let's change this to P. Okay, and basically the explanation is that in order for this to happen, it must be extremely, the nucleus must be extremely small, so that most of the atom is actually empty space. So most of the time it just sort of goes straight through, because most of the atom is empty space. But in the occasion that it actually does hit the atom, it can bounce off in kind of radical directions. So yeah, so that was the experiment by Rutherford. But so in this atom, basically it's composed of either electrons, protons, and neutrons. And what is actually happening in this static electricity phenomenon is that actually some of the electrons are being kind of stripped off the atom and ending up on, say, this cloth here, right? So what you actually end up with is a bunch of atoms, and they're like missing an electron here. So whatever this, well, this is glass, right? So glass is, silicon dioxide, things like this. So so you have some atoms inside this material, and electrons are coming off that material and ending up on this. So the electrons, there's an excess of electrons on the cloth, and there's sort of a deficit of electrons. So this thing, normally an atom has equal numbers of the protons and neutrons, so that they have exactly the same charge, and this is charge neutral. But if you take away an electron, then now this whole thing actually has more protons than electrons. So this will have a deficit of electrons, hence it's going to be positive. Okay, so that's fine. All right, so that's what the charges are. But let me just move this. Okay, and so how do we measure the charge? So the way that we measure charge is in units of so-called coulombs. So named after Coulomb, who was investigating these types of things. And so basically the elementary unit of charge on a single electron is defined as 1.6 times 10 to the minus 19. And because electrons, we decided it was a negative charge, so it has a minus sign, minus 1.6 times 10 to the minus 19. Proton has exactly the opposite, same magnitude charge. So this is how we measure units of charge. And so if you want to have some typical numbers, actually the amount of charge that you might have on a on something that you might have in everyday life is actually pretty low. So the amount of charge, for example, on this sock might be somewhere like in the region of like, say, 10 to the minus 7 coulombs. So of course that's actually a lot of electrons. So this is 10 to the power of minus 7. And so the number of electrons, for example, could be something like 10 to the 12, right? So that's actually quite a lot of electrons. There's quite a lot of electrons, but I mean, in terms of the total amount of charge, it's still a very, very small number. Just to compare it to something that you may be a little bit more familiar with, if you calculate amps, so amperes, right? So one amp that basically means 1 coulomb per second, right? So if you got a piece of wire and then you got a current of 1 amp flowing in it, that basically means that you got all these, what actually happens are these electrons traveling in the wire. Electrons, so as I said, the electrons physically move to the left in this case. So if I say that the current is going to the right, then the electrons actually go to the left. Okay, so this is the confusion that we sort of ended up with because Benjamin Franklin got a 50-50 chance of getting it right wrong. But ultimately what happens is that, say you draw a imaginary line here and say, okay, how many charges are going to flow in that 1 second? Well, 1 amp would mean 1 coulomb per second. And how many electrons is that? Well, that's going to be, for example, 1 over 1.6 times 10 to the power of 19. So that means that in terms of the number of electrons, something like, something like 10 to the 19, so 1 with 19 zeros after it, that many electrons are passing through that point at every second. Okay, hope that is clear. So that's how we measure charges. And if we want to say what's the force, so this lady here has some socks and things stuck to her, right? So clearly there's a force that is actually being exerted on this, otherwise the sock would just fall off, right? So what is that force? Well, how do you work that out? Well, here is Coulombs Law, which tells you what is the force between two charges. So this is not just just for electrons, but say you had like a ball, it's charged with some electricity, and you can work out like what is the force that's actually between these two objects. And the way the formula works is that you have this k is just it's a proportionality constant to get basically all your numbers right? So this produces the right kind of magnitude of force, and Q1 is the amount of charge measured in coulombs on this first charge. Q2 is the charge on the second object. Then R is the distance between them. So basically what happens with this thing is that obviously the more charge that you have, you'd expect the force to be bigger, right? So if you say double the amount of charge on one of these, then you'd expect like twice the force between them, right? Because there's twice as much charge. Now, if you double the charge on the other thing, then of course you'd end up with double the force there too. But if you double it on both of them, then because it's doubled and then doubled again, it's actually 4 times as big. And so this is why it multiplies actually when you have these two charges. So that's why you have this Q1 times Q2 on the top here. Now you have on the denominator, we have this R, and this R is it's actually r squared. And the r squared basically means that the further away you are, the weaker the force is. So because it's a denominator, you know, if you divide by a bigger number, then this whole thing becomes small. So if you take away the charges, then these forces get weaker and weaker. And if you bring the charges together, then the forces are stronger and stronger. And this also works, it doesn't matter whether these are positive or negatively charged. So if you have a plus and a plus here, then what you'll find is that this force is a positive charge, a positive number. And basically what that means is that actually it's a repulsive force. If Q1 and Q2, like one's plus and one's negative, then you can multiply it, and then this will overall be a negative force, and that means they actually attract each other. Okay, so yeah, the interesting thing about this r squared, anybody know, or can anybody think of why? Okay, so Ella is asking what is K? Yeah. So K is this number that is basically just a factor to get the right numbers. So you know, it's well, you know, generally physics formulas always have this kind of factor, because you know, when you put the numbers into this formula, then you know what the role of these things, Q1 and Q2 are, is, and then the r squared, is to basically get the kind of the form of the formula correct, right? So basically has the right behavior. If you think about it, you know, what is you know, what mathematics is trying to do is it's kind of trying to make a kind of a simulation of physical reality, but in mathematics. Like that's might be a weird way to think about it, but you know, just like in the way that, you know, you can simulate a physical reality, you know, virtually, you know, a lot of you do computer science or computer related things, right? So, you know, that's quite a natural concept. But just in the same way that you can make a kind of a virtual version that has basically the same behavior as the real thing, right? I mean, this is a similar relationship to how physics and mathematics actually works together. You know, you have the physical phenomenon, and then you have the mathematics, which basically captures the essential same kind of behavior, but it's a kind of a simulation, if you like, of the physical reality. And this formula is a kind of a, you know, simulation, because these factors here, they have basically the same behavior as what happens in the physical world, right? So you know, basically this dependence of the force as you get further and further away gets weaker and weaker, right? And then, so as a physicist, you think, okay, so what kind of mathematical formula has that same kind of behavior? Well, it's, you know, say 1 on r squared. It's not 1 on r, it's not 1 on r cubed, it's 1 on r squared, because that is the thing that actually has exactly the right behavior as what you have in the experiment. Now, at the end of the day, you have these types of, you know, you have the formula, but then the actual number that you get at the end has to match with, you know, all the conventions and units and all the things that you've done in order to actually get that, you know, that number, right? So, for example, you know, if you measured this r in meters or inches or kilometers or anything like that, obviously you're going to get a totally different answer, right? So there's a kind of there's a kind of a conversion that you need to do in order to get basically the right number here, because obviously if you put in inches, kilometers, meters, you know, you'll get entirely different numbers for this force, right? If you use if you measure this in kilometers, then this is going to be basically much, much, well, okay, so measure in kilometers, then the numbers will be smaller, and then basically this force will end up much bigger. So that actually gets you that right number, and basically all that stuff just goes in to that number such that you basically get the right force as measured in whatever units that you're using. And here typically you're going to use for example forces measured in newtons. I probably done that in the first part of the course. So that's the constant they use. So slightly long-winded explanation, but I hope that answers that question. Yeah, so I was about to ask you guys, this r squared, you might also know that gravity actually also works with a very, very similar kind of formula. So for example, if you tried to work out what's the force of gravity between two objects, this is basically the formula for it. 2 over r squared. Okay, so it's like, this would be an example, would be like, okay, here's the sun, and then here's the earth. Here's the earth, right? And then if you wanted to work out, so what's the force that is exerted on the earth due to the sun, then you'd stick it into a formula like this. M1 is like the mass of, say, the earth, M2 is the mass of the sun, R is the distance from the sun to the earth, and then G is again some constant like this in order to get the force, right? Now, these formula look basically the same. I mean, I've seen memes saying, that Coulomb just sort of copied this formula from Newton, but there's actually a kind of an interesting reason why these formulas look the same. Does anybody want to take a guess at that? And yeah, when you answer, I'd actually prefer that you just use your voice rather than just type in chat, actually. So.
I'm sorry, could you repeat the question a little bit?
Right.
I kind of lost that sentence.
Sure. So the question is, Coulombs law has this r squared on the denominator here, right? This is the formula for the force of gravity between two objects. It also has r squared on the denominator. In fact, the formula looks just about the same. Now, question is, why is it r squared? And also, why are these two formulas so similar? I don't expect you to give a perfect answer to this, so just anything that comes to mind is actually.
I feel like it's because it both describe the attractive or this repel force between two objects, but the first formula is from the macro perspective, and the second formula is from a macro perspective.
I would say that actually for both of them, it could be micro or macro, I'd say, yeah, because this Q1, Q2, this doesn't have to be small. This could be big, or it could be two charges, or it could be big things. Likewise, gravity. I mean, this one for gravity, I think they could be small. It just would be so small that you wouldn't notice it. But yeah. Right. Thank you for your guess. Any other comments?
I can try to answer why is it r squared instead of r itself. I guess the association between the force and the r, which is the distance, is not in natural is not linear. it's not the case that when two objects gets far away, it's linearly decreasing the force. It's like when two objects are moving far away from each other, the force is like decreasing very fast. But if they are very close to each other, the force is not increasing that fast, I guess.
Mm-hmm. Yes. That's I think that's definitely true. So what you said is definitely true. But maybe, you know, it's like, oh, but you know, you might further ask, but then why? You know, why? Okay, so why couldn't it have been, say, just r, or why couldn't it have been r cubed? Go chat. This is a very this is the closest comment that we've got. So hi Han. So you said is it 3D? Yes. So the dimensionality is very important. So what makes you think that it's anything to do with dimensionality, hi Han? Just curious to hear how you arrived at that question,
because I have learned from some books that in the 4-dimensional spaces, the loss of light is proportional to the proportional to the r to the cube. So in in 3-dimensional spaces, it should be r to the square, but
That's
I don't
right.
know why.
Yes. Yeah. Okay. So basically, yes. I think you've basically hit the nail on the head. So it basically comes from this fact. So let me go here. Well, you know, I don't think I can completely explain to you exactly the reasons without really going to some heavy mathematics, but the way that it works is something like this. So say you have like a charge here, right? Now, now it kind of probably makes intuitive sense that any distance, any point that is the same distance from it will have the same force, right? So if you got something here, this is our sort of test charge here, right? Say it's another positively charged thing. Now that will have the same force because it's the same distance from the charge, okay? So then we can kind of, you know, we can try kind of draw a circle here because basically all these points will have the same force, different directions, but still same force from here. And in fact, because we live in a 3-dimensional world, this is not just going to be a circle, but it will actually be a sphere. Okay, so we better kind of try and draw a sphere here, you know, like this. So basically, any point on this will have exactly the same force. Now there's an interesting kind of theorem that comes from well, sort of multi-dimensional calculus, and eventually it says something like that the force times by the area of this surface here. Okay, so all these points with exactly the same area is actually equal to something like, in this case, the charge, well, okay, so say the product of the two charges. And basically this thing here is just a property of the actual charges, right? So this doesn't really depend upon the distance or anything like that. You can make this r, you know, bigger or smaller, and it would still be the same q1 times q2. But what will change is this area actually, right? So what is the surface area of a sphere? Does anybody know?
Pi r squared.
Pi squared. That is the area of a
Four.
circle.
I mean 4 pi r.
I'm after, yeah. What did you say? 4 pi? I think,
R.
yeah, 4 pi r squared, right? Yeah, and the area of a sphere, like surface area of a sphere, is 4 pi r squared. And so basically, in this case, you will end up with something like Q1 times Q2 divided by 4 pi r squared. And this kind of logic also holds for the for gravity as well, because basically also for gravity at some distance, you'd expect like the force to be the same because it's the same distance. So this now goes back to the point that we had from Hai Han. So Hai Han was saying, like, if we lived in a 4-dimensional world, it would be cubed, and that's actually correct, because so if you had a 4-dimensional sphere, what is the surface area of it? Actually, I'd have to sort of sit and work that out, but it'll be, you know, I mean, you can already see here that for a cube, the volume is, what's the volume of a sphere? Anyone?
Four over 3 times
Right.
pi r cubed.
4 over 3 pi r cubed, right? Yep. So, you know, volume is like, we live in a 3-dimensional world. So in 3D, the volume is 4 over 3 pi r cubed. Area is 4 pi r squared, right? So in 2D, so that's basically like a circle, right? So the area of a circle is pi r squared. And then what's the circumference of a circle? Circumference, this one. Can't remember. Yes. Oh, close. 2 pi r. Yep. 2 pi r. Yes, that's right. So, so you can kind of see the pattern here. So, like, in 2D, area is actually kind of like the volume, right? Because area is the sort of the middle bit of the thing, right? So you've got this circle, and then the stuff in the middle is sort of the area, and so that's pi r squared. We live in, if it's 2D, it's like squared. The thing on the outside, which is the circumference, that's sort of the outside part, the power is down by 1, right? So in 3D, the volume, which is the stuff in the middle enclosed by the sphere, is it's the same power as the dimensions, and then area is 1 less power. So you can imagine in 4D, the 4-dimensional volume, which is sort of like the stuff in the middle of the 4-dimensional hypersphere, would be something like r to the 4, right? But here, in terms of this formula, it's actually the boundary, the size of the boundary, and that would actually goes like the cube, right? So the 4-dimensional surface area of the hypercube is actually going to go something like the cube. And so in this case, the force law would be actually, yeah, something like Q1, Q2 over, you know, r cubed, and then there'll be some proportionality constant. Now, another interesting thing. So actually, for my PhD, I actually did something on a hypothetical 1-dimensional model, and you can kind of imagine. So what does it mean for it to be 1-dimensional? Well, okay, in this case, the actual, I don't even know how to call it. So the I guess it would just be length, right? So the stuff in the middle is only like two points here, right? So if you live in a one-dimensional world, so plus and minus r. So essentially, it's just like this distance here. So in this case, the length, which will be a bit like the stuff in the middle. So it's like either the volume area or this is the length, and then the I don't even know what to call it. This would actually be just well, constant. So in this case, I think it would just be I think it would be just 2 in this case. Okay, so because there's just like 2 points, 1, 2. Another way that you can see the relationship between these two things is that if you know calculus, then you take the derivative of this volume, then you always get this formula. So if you take the derivative of 4 pi r cubed with r, then you'll get 4 pi r squared. Take the derivative of the area, then you'll get circumference. So here 2r will give 2. So well, yeah, if you lived in a different dimensions, then you know your rule for like these the forces like gravity and static electricity, these will all be different, basically because of this sort of fundamental relation that goes essentially back to this thing is called Gauss's law, by the way, Gauss's law. Okay, any questions? It's a bit of a tangent, but I think it's a bit of an interesting tangent. Okay, no. All right, well, let's then resume. Okay, so force between charges is some formula that looks like this, K, Q1, Q2. So why don't we just do this question. Calculate the force between 2 charges, one with 2 coulombs of charge, another with 3 coulombs of charge separated by 2 meters. All right, so why don't you just get your calculators out and just do that. I'll give you a couple of minutes. And once you have your answers, just shout them out, I guess. I guess I'll do it too. So, sorry, the question was, whoops, I have stopped sharing. Coulombs, 3 coulombs separated by 2 meters. And you might need this formula here. Wait a minute, have I got these numbers right? Well, hold on. Let me just check that there is no typo here. Well, I guess I'd prefer you to actually put the numbers in so that you actually get some real numbers, because otherwise you don't really have a feel for whether it's the correct answer or, you know. Okay. All right, anybody got any answers yet?
A 5.99 9 time multiply 10 times 10 9 power.
Okay, 5 point something. So, hold on, actually different to what I got. So 2 coulombs and 3 coulombs, right? So you did
2 meters.
2
So
times, yeah, divided by 2 meters, or 2 meters squared. Anybody else got an answer? Okay, we got an answer. Yeah, so 1.34 times 10 to the power of 10 newtons. Yeah, or 13.4 times 10 to the 9. Yeah, so that's what I get. So is that how big is that, do you reckon? Is that pretty big or pretty small? Or average? Yeah, it's pretty huge, right? Because what we know from F equals ma, Newton's laws, that 1 Newton will accelerate 1 kilogram of material by 1 meters per second, right? So basically, like 1 Newton is a pretty like everyday type of force that you could push with, like your hand pushing something will be something in the region of 1 Newton, something like that, right? But this thing is if we put in those numbers, this thing is 10 to the power of 10 newtons. That's an enormous force. That kind of force will probably destroy your buildings, things like that. Now, basically what this should be telling you is that actually the numbers that we put in are probably not really typical kind of numbers, right? Like, so probably, I said that like the charge of sock is maybe like 0.0000001 coulomb. So that's probably more like a typical number for a charge. And so if you put in like 1 coulomb, this is actually an enormous charge. And even though they're separated by 2 meters, actually they that's the amount of force that you feel. So this kind of tells you by actually plugging in numbers and actually getting real results, a kind of a feel for like what's a typical number range of these things. And a typical amount of coulombs that you might have due to static electricity is going to be much, much smaller than 1 coulomb. So 1 coulomb is actually a really, really big amount of charge. Okay. All right. So we've said, okay, so rubbing substances actually create static electricity, but why actually? I mean, let's think a little bit deeper and say, so why does rubbing do anything? What does rubbing exactly do? So basically, this is a kind of a chemistry kind of phenomenon. So basically, all kinds of materials just naturally have a affinity for pulling electrons. And this is just, due to the chemistry of the particular substance. So what I've got here is a table of the periodic table of elements. So obviously these are just elements, so they're the bare, you know, just the single kind of atoms themselves. But what it kind of shows you is that various different types of elements either, you know, would either kind of like to get rid of an electron or would like to attract an electron. And I think so. For example, on the left here, these are the alkali, and alkali metals would very much actually like to get rid of an electron. Okay, so they kind of at any given opportunity, if they can get rid of an electron, then they will. So basically, these ones generally have pretty low electron affinity because they don't really want the electron. In fact, they would like to get rid of one, right? On the other hand, these things like elements like fluorine, chlorine, these have a high electron affinity because when it has an extra electron, it is in a much more stable state, okay, chemically. And basically the reason for this is, again, it sort of goes back to chemistry, but it's to do with sort of kind of stable configurations of electrons. And basically the most stable configurations of the electrons are these so-called noble gases. Things like helium, neon, argon have a kind of the most stable electron configuration. So essentially all these other elements are sort of trying to get into the same type of electron configuration as these noble gases, helium, neon, argon. Okay, so basically, so why rubbing creates this static is ultimately due to chemistry. And so if you have two materials, now these are just the elements, right? Now, if you start to make compounds with these elements, then of course, in particular compound have different electron affinities, right? So just this is just the elements themselves, but each compound, you know, will have a particular electron affinity. And so you have two materials. Now, of course, you know, every single material has a different value of the electron affinity. You can just see that already from these from the periodic table here. So if you put two materials together, then what's bound to happen is that one of them has a higher electron affinity than the other one, right? So in this case, material B just, you know, has a stronger attraction for electrons than material A. And so if you stick them together, then electrons will kind of get captured by material B and they will leave material A because, you know, this is the more chemically advantageous kind of configuration. So, okay, that's kind of explains a little bit more of why you might get static electricity. So in this case, material B is going to end up kind of negatively charged and material A will be positively charged, right? Now, what about the rubbing part? So why are we rubbing? Now, oh, okay, sorry. Right, okay, maybe we'll come back to that one. So what does rubbing do? Well, essentially, if you have a material and this material doesn't conduct any electricity, so these electrons, they aren't free to move. Now, what's going to happen is that you put these materials together, okay, then the moment you put it together, the electrons, they go, okay, well, you know, I want to be on material B, it's much better, you know, much better. So all the electrons go. But then as soon as you get some movement, these other electrons that haven't moved from material A to material B, they're kind of they're blocked here because you've got all these charges, right? And then the extra charges, it's like charges repel, right? So now there's sort of a force that's acting on this one to push it away from these ones. So even though like materially these electrons kind of want to go over here, but they're sort of blocked by these electrons that are already there because, like charges repel. So the answer to that is that you just basically you move this material to a different spot, right? So for example, if you just move this one up here, then okay, then we've got a free spot here, right? Now this electron can move here a little bit more, and then there will be an accumulation of charge there until these electrons block further electrons from coming in, and then we can just move this thing down here, and then more and more charges can go across. So what are we doing here? Well, that's what we call rubbing, right? We're just moving this material to different spots so that it gives maximum opportunity for these electrons to actually go to the other side, right? And then after you do all that, you have all these charges here that have accumulated on material B, and left over, this will be basically, more and more positively charged, because every time an electron goes across from A to B, this will leave it positively charged. Okay, so that I think more or less answers the question of why we want to do, why rubbing stuff actually produces this. It's essentially because of this kind of effect of, these materials have a stronger electron affinity. Okay, now maybe I'll just go back to whatever I was going to talk about here. So yeah, you might have noticed that, plastics tend to, be very kind of static electricity sort of, inducing, right? You've got a plastic bag, and you spend like 5 minutes trying to open the plastic bag because it's stuck together, and stuck together because well, partly because of static electricity. So so basically plastics are a substance. It has a strong electron affinity, so plastics tend to attract a lot of electrical charge. And another reason why, so it's not just the material itself that has a strong electron affinity, it's also because it doesn't really conduct electricity very well. So of course plastics are a excellent insulator. So it naturally has a very, very high electron affinity, so it tends to want to attract electrons whenever it can. And also basically the charges just don't move around, right? So if you've got charges here, this thing will be just sort of covered in these electrons everywhere, and basically they're sort of stuck there because it's an insulator. So that means it can't really move around very well, right? Compare that to something like if you have some kind of metal or some other material, like say have carbon. So graphite is a very good conductor, right? So the pencil lead that you have is actually an excellent conductor. These are also quite good conductors. These are basically metallic materials. Now those materials, even though they have a electron affinity, what would happen is that they would just sort of flow away somewhere, because the electrons are actually mobile. So they're not just like stuck here in one spot and can't move. They can flow somewhere. And so, for example, if this plastic was actually conductive, what could happen is that the electrons start to flow, through this person's hand, and then basically this person is standing on the ground here, and then the electrons can just flow flow away into somewhere else where they are far away from each other as possible. And that's basically what charges want to do because of the forces between these electrons. It's not that these charges, of course, because of the affinity, the electrons want to be with the plastic, but if they could flow elsewhere, then it might be more energetically favorable to do so. So they might flow away elsewhere so that they're nowhere near each other. Okay, so yeah, so this is also why you tend to put in electrical devices in these so-called anti-static bags, because, well, plastics tend to, accumulate a lot of static electricity. And electronic components, and remember I said that some of the static can be, could be up to like 1,000 volts. And so imagine connecting your electrical device to 1,000 volts, it will, obviously it can harm the device. So this is why you put these devices not just in any old plastic bag, but just in these anti-static bags. And these are especially designed so as to, say, not accumulate a lot of electrical charge on them. And some of these bags also are made conductive so that there's this effect called the Faraday cage effect, where it actually kind of blocks any kind of electric field. But I don't think I'll go into that so much. Okay. I think actually this is a good place to finish up today. Any questions anybody had? All right, no questions. Good. Then, so for this week's homework, then please just summarize what we've done in class. And yeah, I think I won't have any extra questions for this week. So just a summary of what we've talked about, and please just hand that in on Brightspace. Okay, so that's it for today. So I will see you all next week then.